Okay, well, run into a little glitch here, so let's see what we got. M times x double prime. X double prime is s squared L of x minus x of 0, s x of 0 minus x prime of 0. And L of x prime is s L of x minus x of 0. Of course, L of x is L of x. Of course, we bring the constants out in front of all of these terms because we have a linear operator. Okay? So we want to solve for L of x. Okay? Well, we have a ms squared L of x here plus gamma s L of x here and a k times L of x here. And now watch me exhibit my incredible clerical skills and mess something up, so keep an eye on me, right? Okay? We have x of 0 here and here with an s times m we have a negative ms times x of 0 and a gamma times x of 0. So we can kind of factor that out, right? And then we have this, okay? Have we gotten everything? Yeah, and I can check off my terms up here and make sure everyone is represented down here. Okay? Let's assume that I got it right. Okay, this tells us okay? And notice that this ms squared plus gamma s plus k is just what you get for the characteristic equation of this left-hand side, right? Except we got an s instead of an r, but your characteristic equation here would be mr squared plus gamma r plus k equals 0, okay? So that comes out of it, and you know, understanding why that mimic of the characteristic equation comes out of this process, so that when you do this, you get it. Well, it gives you a little deeper understanding, whether you have time to develop it or not. Yeah, but if you're working with all these problems and all of a sudden a light bulb goes on, that would be great. But it's not required, okay? But you want to look for those kinds of insights. Okay, now, stuff over here is kind of pestiferous. So I'm going to assume that x is 0 and x prime of 0 are both 0. This means you've got this system and you started from rest at the equilibrium point. Okay? So you start driving it by this function. If it's a pendulum, you start tweaking it when it's at rest at equilibrium. Okay? And if it's some other kind of system, it's an electrical system, you know, you start it where you have no voltage in your capacitor, so there's no current in the system. I said so, there's no voltage in the capacitor and no current in the system. you'd have a current in the system with no voltage and capacitor, inductor energized, driving a current. So you just start it from its simplest rest state, and then you start driving it, okay? So, you make the simplifying assumption this system's at rest and equilibrium, okay? That would be like opposed to a pendulum that's out at its extreme point, ready to swing back, which is totally analogous to having an inductor charged up, an inductor carrying a current. Okay. But that's something, since you haven't had physics, you kind of want to store away for when you do. Okay.
They're just talking about potential energy.
Sorry.
They're just talking about potential energy.
Well, yeah, it's you know, the potential would have zero potential energy. Yeah, you could say equilibrium, okay? Is equivalent if you put the potential energy zero at the right point to having no potential energy. But the equilibrium point's actually defined in terms of potential energy, okay? It's the point from which, if you move in any direction, well, stable equilibrium, I could say stable equilibrium. A stable equilibrium is one where you move in any direction, you increase your potential energy. Okay? So, yeah, go ahead and put that word in there, should have thought of that. Okay, stable equilibrium. Okay, well, anyhow, there's your simplifying assumption. And now we get a very simple okay? This denominator doesn't depend on what you're driving it with. Okay? So you're going to call this thing 5s times the plus transform of f of t, where 5s is just 1 over ms squared plus gamma s plus k. And this thing's your system transfer function. And now you can use this if you can observe the system for any function, okay? And determine the Laplace transform of that function. You can find your system transfer function, which will then tell you how the system behaves for any function, okay? So we want to kind of turn things around and see if there's a way to determine this function from information about a known function and its transform, okay? So we're going to take a look at that idea. So go ahead and take your note on that.